We present Avat3r, a large animatable reconstruction model for the creation of high-fidelity 3D head avatars. Our method predicts avatars from 4 images in a single forward pass, eliminating the need for costly fitting or test time optimization. Given only 4 images from a casual phone scan, Avat3r performs a sparse 3D head reconstruction. The resulting 3D Gaussian representation is animatable, offering full control over facial expressions. Once the avatar is generated, it can be driven at interactive frame rates. Notably, our model has never encountered this person's specific facial expressions, yet Avat3r produces realistic animations and plausibly inpaints unseen regions. The entire process, from capturing the head with a phone to generating the final avatar, can be completed within minutes. At a high level, Avat3r takes 4 posed images of a person as input and predicts 1 3D Gaussian for every pixel. For each input view, we leverage position maps from DUSt3r and feature maps from Sapiens. These inputs are processed in a vision transformer backend to infer 3D structure. Facial motion is modeled with cross-attention to a sequenced expression code. We also add skip connections to the predicted position and color maps to simplify the model's task. Finally, all Gaussians with sufficient confidence will be fused together to form the final 3D head. Notably, our design does not rely on a template mesh, allowing Avat3r to accurately model complex features like long hair and facial accessories, which are challenging to represent with a standard mesh topology. To train Avat3r, we require 4 input images and 1 image for supervision with its corresponding expression code, all taken from Avat256, a large multi-view video dataset of human heads. We compare our method with GP Avat3r for avatar creation from 4 input images. The avatar generated by our method better resembles the target person compared to the baseline. Furthermore, our renderings are fully 3D consistent and free from temporal flickering. Avat3r generalizes well to rare appearances. Both blue hair and the headband are preserved, while GP Avat3r fails to reconstruct them. We further showcase Avat3r's generalization capabilities by creating avatars from people from the Ensemble dataset. Note that this dataset was not used during training and contains images with entirely different lighting conditions, viewpoints, and camera properties. Despite these differences, Avat3r generates realistic 3D head avatars. We evaluate the impact of various components in our pipeline. Without the DUSt3r position maps and the Sapiens feature maps, the generated 3D representation is misaligned and blurry. Sapiens feature maps improve overall sharpness, while DUSt3r maps enhance the alignment of small details. We also examine the effect of inconsistent input images, where the model expects identical expressions. The result is severe misalignments. This situation can occur when expressions accidentally change during a casual phone capture. In contrast, our full method produces sharp and aligned renderings even when the facial expressions in the input images vary drastically. While Avat3r is designed for 4 input images, it can also work with a single image. To achieve this, we employ a pre-trained 3D GAN and perform 3D lifting on the single image. From the lifted 3D representation, we render the 4 input views required by our model. The resulting avatars can then be animated with a wide range of complex expressions. Here, we showcase several single-shot avatars. Even in this heavily under-constrained scenario, our method produces highly realistic avatars. We compare Avat3r to GAG Avatar for avatar creation from a single input image. Our method is fully view consistent and generates much more realistic expressions compared to the baseline. Finally, we show more application scenarios of Avat3r. Our method can animate heads that were randomly sampled from a 3D GAN, essentially making any static 3D GAN animatable. Avat3r also generalizes beyond real faces, such as an image of a fairy tale woman generated by a diffusion model. Avat3r's animation capabilities even extend to highly out-of-distribution inputs, like the images of antique busts or iconic paintings, such as the Mona Lisa. Thank you for your attention.